We're going to be looking at continuous random variables. We've already looked at discrete random variables where we have a table of values which are finite. We could count how many numbers are on the table. Now we're going to be looking at infinite. So instead of using a table, what we're going to be doing is using a density curve. There's multiple types of density curves. We're going to be looking at just two today. One is the uniform distribution, and that's just a normal rectangle where we have a base and we have a height. Now I'm going to be using the area model is equal to the probability. Those are very similar models. So I'm going to use area and probability interchangeable. And we know that all the probabilities add up to 1. In the same way, the area of all density curves also add up to 1. So what we're going to do is we're going to find the height of our density curve. It tells us that our density curve has a length of 2. So if it has a length of 2, that means the height has to be a half. And the reason why is because our area has to be equal to 1, and we know that 2 times a half is equal to 1. So our height is a half. For the next one, we actually have our density curve, and we're trying to find the probability that it is less than 1. So we figure out where 1 is, and what we're going to do is we're going to find the area of that shaded region. So this is going back to geometry where we take the base and we take the height and we multiply them, and that just gives us a half. And remember, just like what we solved for on the last one, our height is a half. So with the next one, this is a little bit different because when we're looking at this, notice that it's no longer less than, it's now greater than 0.5. So we figure out where 0.5 is. It's just an estimate. We want everything greater than that. Remember, it ends at 2. So when we're talking about the area, we're talking about a base of 1.5, and then a height, it's the same, it's a half, and that gives me 0.75. Now for the next one, we do the same thing, and we have 0.2, and we have 1.4, and we're trying to find in the middle. So when we're finding the area, what we do is we find the base, and between 0.2 and 1.4 is 1.2, and we have the height, which is a half, and that gives us 0.6. So let's look at the next example. For the next example, what we have is a uniform distribution, and this time it has a length of 6. So if it has a length of 6, and remember our area is equal to 1, that means base times height equals 1. That means the height has to be 1/6. So we're going to take that information for letter B. This time it's greater than 4. So we have 4 to 6, and that, of course, has a base of 2, and the height is the same. We just found it, 1/6. You could keep it as unreduced or you could reduce it, whatever you prefer. Both answers are correct. For the next one, this time it's less than 2.5. So we have 2.5, it's everything less than it. So that means that our base is 2.5 and our height is the same, it's 1/6. I'm going to round the answer here because we can't have a decimal fraction. Either we can have a fraction or a decimal. So I'm going to put 0.42. And then for our last one, from 1 to 5, what we have is starting at 1, ending at 5. And once again, we're trying to find the area. So area is equal to, our base is 4, our height is 1/6. So that right there would be 4/6, or we could reduce it to 2/3. Now, we're going to be looking at our standard normal distribution. We're going to be using the conversion z equals x minus the mean divided by the standard deviation. So the Greek letter mu is equal to the mean or the average, and sigma stands for the standard deviation. And what we're going to do is we're going to follow the standard normal distribution, and this represents all distributions. We have the mean at 0, which is the middle, and it is separated by standard deviations. And so what we have is one standard deviation is 68% of the data. Two standard deviations is 95% of the data. And then when we're talking about three standard deviations, what we're doing is we're talking about 99.7% of the data. Now, why we use a standard normal curve is because we have different groups of people in different normal distributions. And what we're trying to do is we're trying to see the best overall based on their standard or on their normal distribution. So we're going to be looking at 4 baseball players, and we're going to be trying to find which one is the best overall based on their time period. So Babe Ruth has a certain normal distribution that has a mean and a standard deviation. So does Roger Maris, so does Mark McGwire, and so does Barry Bonds. So our z-score takes all the normal distributions and converts it into the standard normal, and we could see whoever has the best z-score or the highest z-score would be overall the best player in terms of relationship with other players. So I'm going to put BR for Babe Ruth, and his z-score would be 60 minus 7.2 over 9.7. So I subtract the x from the mean divided by the standard deviation, and I get 5.44. That means he's over 5 standard deviations above the mean. So he's way beyond most players. Remember, 99.7% of people are in between -3 and 3, so 5.44 is phenomenal. I'm next going to look at the z-score for Roger Maris, and it would be 61 minus 18.8 divided by 13.4, and that right there gives me a z-score of 3.15. Once again, better than 99.7% of the people, not quite as good as Babe Ruth in terms of the population that he comes from. But notice that he does have more home runs. Because there's more home runs overall, that's why we're considering Babe Ruth a better player in relation to the other players in the league. So the next one we're going to look at is Mark McGwire, and that would be 70 minus 20.7 over 12.7. And so Mark McGwire would be 3.88. Once again, almost 4 standard deviations above the mean. Phenomenal player, still would be considered not as good as Babe Ruth in terms of the players at that time. And so the last one we'll look at is Barry Bonds. Once again, if we're looking at just the actual numbers, Barry Bonds has the highest number of home runs. But in compared to his group, we're going to see what it looks like. So the average is 21.4, 73 minus 21.4 divided by 13.2 gives us a z-score of 3.91. So we could see that Barry Bonds clearly is better than Mark McGwire and Roger Maris, but we would have to say overall, Babe Ruth would be considered the best in terms of all the players in his league.